To welcome everyone for taking the time today for joining us for this ACRS presentation by Dr. Mark Baird from CSIRO. If I can just ask everyone to make sure they're on mute, please, and feel free to prime your questions for the end when we'll obviously have some Q&As, but of course also feel free to use the chat function as we go if there are specific questions you want to leave as a placeholder. To start with, I'd like to acknowledge the traditional owners of the land on which we're all respectively streaming in from today. I'm on the lands of the Dharawal Nation, and on behalf of ACRS, I pay my respects to their ancestors, their descendants, who continue cultural and spiritual connections to country, and we recognise the valuable contributions to Australian global society. As I said, it's our great pleasure today to welcome Dr. Mark Baird, and thanks for his time today for presenting his really exciting work. Mark is a principal research scientist at CSIRO based in Tasmania. He's an ACRS fellow awarded in 2020. And Mark's actually had an extremely colourful career to date already, and I'll keep this brief. I'm sure you'll all want to cut to the chase to hear Mark's presentation, but really just as a segue of some of his achievements, Mark has been appointed through various postdoctoral fellow roles at UNSW and UTS before being appointed as a senior researcher for CSIRO. Prior to that, he did his PhD in the UK, all of that really stems from his interest as an aquatic scientist. He uses observations and numerical models to study both estuarine and marine systems. Spans a vast array of topics, including biogeochemistry, estuarine ecology. I've actually collaborated on Mark on a couple of papers looking at phytoplankton biooptics, for example. But really that interest spans even more diverse to include coral reefs, ocean acidification, and certainly a focus at present with water quality and water quality management. So Mark leads the CSIRO Coastal Biogeochemical Modelling team, key developer of the CSIRO Environmental Modelling Suite, and developed numerous parameterizations for ecological processes. Importantly, Mark's led the team that's developed the coupled hydrodynamic biogeochemical model of the Great Barrier Reef that we all know as eReefs, which is a fantastic platform if you've not had the opportunity to use it or check it out. And that's used by both the state and federal governments to assess the present state of the reef. He's had deep connections in the past through IMOS and through other biooptical roles, including biooptical working groups, both nationally and internationally. His current role through CSIRO also deeply connects him into RAP through modelling temperature and light stress through novel interventions. And when Mark was asked to present and kindly accepted, I did ask him for a fun fact, and he provided me with this this really intriguing point that when he first visited Townsville in 1994, it was actually to fix some heat exchangers at Clive Palmer's Queensland Nickel. So he's obviously got deep connections to mining and water quality right from the outset, so he can certainly present from deep experience. So without further ado, I'd like to hand over to Mark for his presentation today.
Thanks, Dave. I'll just share screen. And now it's paused. There we go. Okay, have you guys got that?
Yep, that's all great. Thanks, Mark.
Okay, well, yeah, thanks, Dave. And it's good to be able to present this work. It's the work of a lot of people, in fact. And so also given the sort of, I think, importance of the topic, I'm going to stick pretty closely to the peer-reviewed publication that we all came up with, because I think important to keep that peer review strength behind us. And so the paper that it's coming from a lot from is from this paper in Marine Pollution Bulletin in the special issue for John Brodie. And so, and I think in a way, each of the co-authors is really a co-author of this talk. So, so thank you to all the different contributions from those co-authors, and also for the funding from Great Barrier Reef Foundation, and then I guess the other collaborators in the ACRS project, including Queensland Government, Office of the Great Barrier Reef and Department of Environment Science, AIMS and the Bureau have all had a role in this. So thank you to everyone for that. Okay, so it's actually quite a difficult thing to determine the impacts of catchment-derived nutrients and sediments on marine water quality. And just to sort of have a fun introduction to how hard it is, if you look into the entries in when the Endeavour moved up the Queensland coast in the respective journals of Joseph Banks and James Cook, you find that that Banks was there, and he. So this is just as they're moving north past Moreton Island, and so Banks records that he sees a dirty clay colour of the water, and suggests that it's as a result of a freshwater plume, and that there must be a large river nearby. And in contrast, we find that in quite a condescending manner, if I'm allowed to say that, Cook then says that he thinks it's got nothing to do with the river, that it's that the colour of the water is without the assistance of rivers, and quite like his phrasing of some on board were of opinion that there was a river. So quite condescending, in fact. Of course, we know a lot more now, but the challenge of distinguishing between what is catchment-derived impacts on water quality and what's local reef suspension is a difficult task. Nonetheless, I'd like to just go through, of course, some of the information that we have got, just a small subset really, that tells us that in fact catchment nutrients and sediments does have an impact on the water quality. And so firstly, this paper from Katharina Fabriskas and co-authors. So she was looking at in situ measurements at light penetration. And of course, she found that she could correlate the light penetration to both the through a year as well as between year river discharge. So clear evidence in the water of the impact of catchment nutrients and sediments. Of course, remote sensing is another key tool we have. And one of the interesting things about in this study, they're looking at optical plume extent. And of course, if you've got an optical change, then that is a change in water quality in the water. So it's a direct use of remote sensing to look at the impact on water quality. And again, they found a good correlation between the wet season discharge and the area of plumes. And a third study, just to highlight this again, comes from Steve Lewis and co-authors who are looking at the ratio of barium, which is coming from the catchments, and calcium, which of course is uniform throughout the ocean. And so they of course found that mineral mixtures laid down, and additionally luminescence of these coral rings, the different layers within the corals, that they could correlate those mineral mixtures to the exposure to catchment-derived constituents, which is co-varying with the rainfall. So you can see in their picture there, strong Burdekin discharge equated to a an increase in the barium to calcium ratios and the luminescence. So there's many more studies like this, but I wanted to come to this one last because I can start to introduce the role that numerical modelling might have. And so what I've done here is this is one of the barium and calcium ratio observations from Pandora Reef. And so on the left, you can see where Pandora Reef is at B, and at A, where the water came from in the Burdekin. And so this is during the big floods of 2011. And so they took measurements of the barium concentration in the Burdekin flow at the time. And so if I put that barium concentration into a numerical, into the eReefs model, and then of course watched it propagate out in a river plume, but also be diluted both horizontally and vertically. If I then calculate what the ratio of barium to calcium would be at the site where this core was taken, then you see the green line, and you can see this matches really quite well with the observed barium and calcium ratios at that point. And so the point to make here is that we've gone beyond just correlating this this terrestrial signal with river flows, but instead we're actually calculating what the impact would be from the river flow at that location. And so this is just one constituent. The modelling that's going to come is going to consider lots of constituents coming out of these, out of the rivers. Okay, so the aim of this seminar, so while the field remote sensing and coral studies that I've just shown provide evidence of impacts of catchment-derived nutrients and sediments on water quality, they struggle to get a couple of things which are really important for managers in order to determine what should be done in the catchments. So they struggle to separate the impact of local drivers of water quality, such as resuspension, from natural, and especially from the difference between natural and anthropogenic catchment-derived drivers of water quality. They struggle too to isolate the influence of different rivers on a particular site. And then also, of course, it's not possible through observations to quantify what the impact of a proposed land use would be on water quality at a future date. So the aim of this talk is to show that with scenarios developed using this process-based catchment and marine modelling system that we have in eReefs, that we can fill these knowledge gaps. Okay, so to describe the modelling thing, it's actually quite a large task, because in order to run the hydrodynamic models within the water column and also the catchment models, we need to have a global ocean and atmosphere model. These come from collaborations with the Bureau and CSIRO. Those weather conditions are then put through the GBR dynamic SEDNet model, which I'll describe a little bit later, and has come from the Queensland Department of Environment and Science. Those loads are then put into the eReefs model, and I've just shown here in the centre bottom the river plumes that are generated in that by that hydrodynamic model, and then those that circulation with the loads from the dynamic SEDNet are then put into a biogeochemical model, which has a whole range of transformations from nutrients into phytoplankton and a whole coral and seagrass and macroalgae in the bottom as well. And so we're just going to go to that stage in this modelling system, but to point out that it has been used for, in different modes, also for report carding, the GBR report card. Okay, so just to look at the marine model in particular, and what I really want to show is that many of the processes that we understand to be occurring that result in impacts in water quality are resolved. So the model tracks dissolved inorganic nitrogen, carbon, and phosphorus here on the right. That's of course taken up by 4 different phytoplankton types. There's zooplankton grazing on the phytoplankton. The death of these all generate detritus. Detritus can sink. That gets into the sediments where it's remineralized back into inorganic forms. We also have corals, seagrass, and macroalgae growing on the bottom. And so if you think about a couple of processes that we might want to represent, so for example, it can track dissolved nutrients delivered in the river plume. So that's coming into the model as a dissolved inorganic phase, but then is taken up by the phytoplankton. So that's one of the processes that we would hope to represent. But perhaps a slightly more complicated one involves particulate nitrogen that then comes out. Of course, it's both affected and sinks. The seabed, there's some, and within the seabed, there's some oxygen-dependent remineralization, which releases some component back as dissolved inorganic ammonium, but actually some of it's also denitrified as well. There are a whole lot of complex processes which we think are representing where these loads from the catchments are going. So catchment management policymakers need to know the effect of river loads on water quality. And so I think the guiding thing over the last decade or so has been the Reef 2050 Water Quality Improvement Plan, which is a large commitment to improve catchments to get better water quality. And it's interesting that you can actually think of how they've gone about these catchment management decisions or strategies. Really, there's 2 approaches which we'll see contrasted as we go through this talk. And so one of them is to determine the minimum reduction required to meet a particular water quality standard, like for example, 0.45 milligrams of chlorophyll per metre cubed might be one of them. So you want to reach a certain standard at every point. But another approach which is taken is to say, well, let's work out what we could achieve with a particular land practice, and then see what those loads delivered from that land practice would generate in the water column. And so we're going to look at how both of those work in this talk. Okay, and so of course there's the key to all of this is the loads that are produced by the GBR dynamic SEDNet model. So thank you to Dave Waters and Rob Ellis, who've generated these outputs. And this has been used for many years. It's part of the whole Paddock to Reef program. And at the end of this talk, I'm going to give you reference to the paper that really nicely describes all of this work. But anyway, I'll summarize what's necessary to understand the water quality changes. So the dynamic SEDNet predicts loads of dissolved organic nitrogen, particulate and particulate N and particulate P, and also total suspended solids. And it's doing this at 35 different locations. How do they achieve this? They have 6 regional configurations of their dynamic SEDNet for each of the regions. And these represent sub-catchment scales down to 50 kilometres square. Within the model, of course, it's generating nutrients and sediments from different land uses. And those land uses are distinguished between grazing, conservation, forestry, etc. And most importantly of all, they've got the ability to change the land uses to reflect new management processes, and in particular, different standards of land management. And these are specific to each of the different land types. So there's a different one for bananas versus cane, etc. So that's the tool we have to play with. And so they've generated a number of scenarios, and it's those scenarios that I use. So the scenarios they have, and we'll be using these all through the rest of the talk, they have so I'm going to call it Q3B or baseline. So this is the best estimate of the total loads of nitrogen and phosphorus that have come out into the ocean in the last 10 decades. They also have a Q3P. This is the pre-industrial or natural loads. And so they restore the catchment. It's vegetation. They leave the dams in place. But they restore the catchment to what they understand to be the original condition and recalculate the loads. And so we're going to define anthropogenic loads as the difference between the estimate of today and the natural loads. And so then we've got 4 scenarios which involve different approaches to improving the catchment. So there's the first one, which is the Reef 2050 Water Quality Improvement Plan targets. And so that's the one that we're presently working with through Queensland Government has done some regulations that involve the outputs of these targets that we developed. But beyond that, they've also got 3 other different catchment scenarios which involve applying innovative, which is the highest level, best practice, and minimum standard land management. And then finally, in order to improve the understanding of the model, we've also done a simulation Q3O, which involves no catchment loads at all. So we've taken the rivers out of the model, or at least the nutrients and sediments from the rivers. So if you now want to think what would be the impact of river loads, well, that would be the scenario Q3 and either B, P, R, A, B, or C, minus the baseline load, the Q3B. So that would give you the impact of the loads in each of those scenarios, river loads. And if we wanted to, that's the impact of the reduced river loads. And if we wanted to look at the impact of the total of all the river loads, then we do Q3X minus Q3 0. So that'll come a bit clearer as I go on. Okay, so I'm straight away just zooming into the Burdekin region, and I've given you this panel of many different animations. So to take you through it, first of all, in the different rows, we have 5 different water column metrics. So I've got dissolved organic nitrogen in the top, chlorophyll concentration, these are all near surface concentrations, total suspended solids, Secchi depth, and then bottom photosynthetically available radiation. And on the columns to the left, leftmost, we have the baseline scenario. So this is our best estimate of what's happened in the last decade. The next one along is when we remove the anthropogenic loads. So that's Q3P. And then we have the targets, the water quality improvement plan targets is Q3R, and then the different standards A, B, and C. And so just quickly, you can see that that if we look at the baseline loads, for example, we see that there's slightly more chlorophyll than in the other cases, but actually we need to look quite closely, and so later on I'll do the difference. Again, with the sediments, there's more sediments. Secchi depths tend to be shallower in the present loads, and bottom part to be lower. So I'll just take you to the next figure. Now what I've done in the next figure is just come closer into those top three metrics and taken at a particular date when the river plumes were strong. And so again, on the left, we can see the chlorophyll surface chlorophyll concentration. And then in the pre-industrial, you can see quite a change in the surface chlorophyll concentration in the pre-industrial. Now, it's a good time to point out, firstly, that they all have the same hydrodynamic circulation, because they've got the same river flow. It's just the nutrients have been changed, not the flow. And of course, they've got the same atmospheric and oceanographic, offshore oceanographic conditions. So you expect the shape of these different plumes to be the same, but the intensity of things like chlorophyll and total suspended solids to be different. And so we can see that if we do remove anthropogenic loads from the catchments, that we get at this point in time, we get quite a reduction in chlorophyll concentration. And so now what I've done in this figure is I've taken away the baseline one, so you see one less column, and instead what I've done is I've done the difference between each of those load reduction scenarios and the baseline. So this is the impact of reducing a load. And so you can see that in the pre-industrial, so now we're looking at the leftmost second down chlorophyll concentration. This is the case where I've removed all anthropogenic loads, and as a result of that, the chlorophyll concentration is reduced. So you can see that it appears as a blue. And if we go down, you can see quite big changes in Secchi depth, which are very sensitive to changing loads, and also, sorry, but that's an increase in Secchi depth, that's why it's red. So you reduce the loads, you increase the depth at which the light goes down. And of course, you get more light at the bottom. And I mean, one thing to point out here is how well the different load reduction strategies have worked. And so you can see that in the case of, so green means no reduction in, no change in the water quality metric as a result of the changing catchment loads. And so you can see, particularly offshore, in all cases where the river plumes aren't reaching, that there's virtually no change in those metrics. And it's only in close where of course, the catchment loads come out in the river plumes that we see a change. And you can see, for example, that there's even with if we take all of the catchments to a minimum standard, that we do not get a very big change in the chlorophyll concentration at this point. So we're going through 2011 in this animation. But that if you go to a higher standard of catchment repair, such as the B standard, which is the best practice, or further the innovative, the Q3A, you can see quite a large change in the water column properties. Okay, so one problem with this is that it's quite dynamic, this where the river plumes go. And so if we're to try and estimate the impact of these catchment reductions, then we're going to see it over a large area in the big flow years, but over a smaller area in the low flow years. So one way to deal with this temporally varying footprints is to actually just look within the plumes themselves. And so how do I track these plumes? Well, what we do is we put a river tracer, if you like, into the model. So in the flow of each of the rivers, I've put a numerical tracer that then gets moved into the water column and vectored and diffused with the rest of the water. And so it goes in with a value of, say, 100%. And so what you can see here with the different colours is how each of those rivers propagate out into the water column. And right now it's in July of 2011. Of course, that was the biggest year. And at that point, actually, you might be amazed at how far the Fitzroy River went. Now, so these boundaries between white and the colours represent the 1% contour, if you like. So it's not a strong influence of the plume, but it nonetheless is, it's quite broad. And the reason I chose 1% actually is because I think on average, the catchment flows have about 100 times the nutrient concentration as the ocean in which they're flowing into. So I think this 1% is quite a good edge of these plumes, if you like. And so now that we know where the plumes are going, we can look within each plume at what the effect is of each of the different catchment scenarios. And so we're using this river tracer to define the edge of each river plume. And for each load scenario, in this case, what we're doing is we're subtracting the chlorophyll in the no load scenario just for the regions inside the plume. And so the figures that I've got on the left here for chlorophyll A, total suspended solids, dissolved in organic nitrogen, and plume area are for the Fitzroy in 2011, reminding you that the Fitzroy was enormous discharge in 2011. And so you can see at the beginning of the year, so if I take you to chlorophyll on the left, the colours of each of so it runs the whole year, and it's chlorophyll concentration on the y-axis. And I've got 6 lines, which are each of the scenarios. And so you can see that the black line is the highest one, right? And so when it reads 0.3, for example, in late January, that's a 0.3 difference in chlorophyll concentration throughout the whole of the Fitzroy River plume compared to the no river load. So this is chlorophyll that's not been naturally out there. There would have been some chlorophyll that would have been there anyway without the river plumes, but this is the component due to the rivers. And so the black one, it can be up to 0.35 in this case. So that's the baseline. So we think that up to 0.35 chlorophyll was added on average through the large area of the Fitzroy plume, but reducing down to say 0.1 later on in the year. And you can see that the action of going to removing all anthropogenic loads, very significantly reduced the chlorophyll concentration, the added chlorophyll concentration due to the natural loads. That was more like only 0.05. And in between is the different scenarios that we used. So that's 2011. If we go and look at it over a longer period of time, so now over the whole time series that we had, first of all, you can see our plume extent down in the bottom right. You can see how the plume area was so much larger in 2011 than it was through the rest of the time. And this is going to become important as well. And then in general, the difference as a result of, so now looking on the top left in the chlorophyll A signal, you can see that at times within the plumes that there was up to 0.6 milligrams of chlorophyll per meter cubed addition due to the total loads, and that if we remove the anthropogenic loads, we could bring that back down to 0.05 previously, or later in the time series 0.1. It's interesting that in the lower flow years that there's greater change in chlorophyll concentration. And this is occurring because, of course, the plumes are much smaller. And so even though the concentration change is larger, the impact on the whole GBR is smaller. So this is a problem for us, and we can look also at suspended sediments and dissolved organic nitrogen. And I can also look at the many different rivers where each one will have a different impact. And you can go to the paper where you'll see this for all of the rivers that we considered. But we've got a problem here in that if I look back at this figure here, you might think that the greatest impact of catchment loads was during dry seasons, when of course it's actually more in the wet season. So how do we overcome this? Well, so for us, I should say, before I overcome that, I can now look at the change in chlorophyll concentration due to river endpoints in the footprints of all the rivers averaged over this period. And when I do that, so this is the change in chlorophyll concentration, right? You can see that anthropogenic and natural loads, so here I've got the scenarios as columns and the rows as rivers. You can see that anthropogenic and natural loads added 0.21 milligrams of chlorophyll on average along the whole GBR due to all rivers, although some of them, for example, the Normanby was, was very small, whereas say the Burnett was much larger. But actually natural loads added 0.11 milligrams. And then I'd like to make the point, and we'll come to this later again, in comparing the different scenarios, we can see that using best practice, Q3B, resulted in a 0.18 change in chlorophyll concentration in the surface from a no loads situation, which was quite similar to the Q3R, which is the targets, the water quality improvement plan targets. So even though these were very different approaches, one was specifying a target for water quality, the other was practice in the catchments, that they come up with a reasonably similar result, certainly when averaged over all of GBR. Okay, but now I wanted to, I suggested this problem that if we have during the dry years, because the plumes are smaller, there's a more concentrated change. So now let's change to not just considering the concentration in a plume, but the total change in chlorophyll content overall over the whole plume. So this is basically taking the area of the plume multiplied by the concentration, and we're just doing it for the surface meter, the top meter. Okay, and so then this becomes chlorophyll content. Okay, and so now you can see when we do this, and so this is actually a sum of each day for these 8 years. So the numbers sound very high, but that's because it's a sum of 8 years of a daily sum of 8 through 8 years. So we can see that in the baseline condition Q3B, that the change in concentration for having no rivers actually added 8,643 tons of chlorophyll. But had we gone back to natural loads, that we only added 4,012. So the amount, so obviously the difference between that is how much the anthropogenic loads added to the chlorophyll content over all river plumes over those 8 years. And that again, we can look at whether the best practice, Q3B, is similar to the water quality improvement plan targets, and in fact, they are quite similar. And then just as a final point to get from here is that the Fitzroy plume actually contained 40% of the chlorophyll content of all plumes from 2011 to 2018. And most of this, we've already learned, was in that first year. So clearly, the water quality is most impacted by the largest flows and the biggest rivers. Okay, so just to break out of that very numerical description of the results, which of course are very useful for people setting loads for policymakers, but we can also jump out and think of some of the scientific questions that someone might ask. And I was asked this question, so I thought I'd just show you how we can use the modelling output to answer it. So the question is, what is the impact of reductions in catchment-derived anthropogenic particulate nitrogen loads on the nutrient supply to the COTS initiation zone after the 2011 flood? So quite a specific question. And of course, this particulate nitrogen is coming out and it's being advected, it's dropping out, and then it's being remineralized in the sediments. So what I could do was look at the difference between, so this was again the influence of the different load reductions. Okay, so the baseline ones disappeared, and these are all the effect of going from baseline to pre-industrial or the targets or A, B, and C. So they're all reductions, of course. And what I'm looking at is the flux of ammonia out of the water column, which out of the sediments into the water column. And of course, this is what's being delivered indirectly by the particulate nitrogen coming out of all of the different rivers, getting itself into the sediments and then remineralizing. And so, and you can see Lizard Island, I've just shown there. And so you can look around Lizard Island and you can see that if we change to a minimum standard of catchments, that we won't impact the COTS, the nutrient delivery from the sediments as a result of the catchment changes in particulate nitrogen. We don't get a very big effect if we use just the minimum standard, but as we go to the higher standards, you see a bigger change in that flux and therefore nutrients available for phytoplankton and in the COTS zone and everything. So many questions like this can be answered now that we have these scenarios all undertaken. Okay, so look, thank you for listening. I'll probably summarize the biggest points that I think come out of this, and maybe it's not quite for policymakers, but I feel like it's the biggest points. First of all, it's clear that there's already multiple lines of evidence demonstrating the impact of catchment nutrients and sediments on GBR water quality, and this is adding another line of evidence. Interestingly, so we went through and we had two different approaches: the water quality improvement plan target approach, which optimized basin-specific targets for water quality outcomes, and this was very different to a uniform catchment management practice, which was for which we had three different versions. Nonetheless, despite these differences, the best practice approach and the water quality improvement plan targets produced actually quite similar improvements in GBR water quality. I think this is a really important result, and this is good news. It means that catchment management can improve water quality on the GBR, and in many cases, the best practice approaches that we know already will actually meet the water quality goals that we've set in the Reef 2050 Water Quality Improvement Plan. So thank you again, and I've just provided a slide here to say there's a lot more additional information, particularly in these two articles in the Marine Pollution Bulletin, and read them together and you really get a great idea of what we've done. And there's actually, and as well as that in the supplementary material, there's a whole lot more different results so that you can bring it down to a particular region that you'd be interested in or river, etc. And so on that note, I'll say thank you and any questions, and I'll stop sharing.
Thanks very much, Mark. That was a fascinating presentation. I have learned a lot in the last 40 minutes, I have to say. I would like to obviously open up the floor for questions. I have some questions of my own, but I'm here to chair any questions that our audience today has. So I will start scrolling through in case anyone wants to raise their hand and ask Mark a question. Maybe while we're waiting, Mark, I'll ask one of my questions. I think one of the key, it seems that so much has been achieved, and it's very positive and optimistic outlook, actually, based on the analysis that's been done today. what are the next steps for in terms of modeling? Are there key parameters that are still yet to be input into the model, and are there also sort of key data gaps in really validating some of the parameters?
Well, I think, I mean, the E-Reef model, can be used for more things than just water quality. And I think there's a lot more to investigate. Parameterized of coral bleaching, for example, is one that, I'm very keen to put in more, detail and improve the model in. I think when it comes to water quality, I think because the model came from that and that was its purpose for the last 10 years, I think it is really actually in good shape to be answering these questions. And I think the next step, which GBRF is already thinking down, is to, we've looked at GBR-wide scenarios in this study, but, investments initially don't equal GBR-wide changes. And so I think looking at individual investments and what they might make, and, the GBRF has a $200 million investment in the Baird region, looking at the impact of that, I think is the next step, because it'll get closer to the actions that are likely to be undertaken, in the next few years.
Great, thank you. Maria Bernard, a hand up first.
Hi, great talk, Mark. I did put it in the chat. I'm just wondering about the salinity and how that tracks those plumes. You can do chlorophyll. Can we match those chlorophylls with salinity?
So, I mean, the hydrodynamic model is compared to salinity at lots of different locations. And so, that's quite a good measure. But of course, salinity is changed by things that aren't just river inputs. And so that's why I put the river traces in there, to get actually what's coming out of the rivers, and didn't want to include things like precipitation and evaporation once it got into the ocean. So so I think sort of to answer your question, I think the hydrodynamic model has been compared to these salinities very well, but I then want to use these traces when I'm comparing to water quality metrics, because that's really an indication of what's come out of the catchments.
Katerina Fabricius also had a question.
Yeah, thanks. Thanks, Mark. Great talk. I've got a couple of questions. One is, in the last slide, you showed the particulate nitrogen as ammonium flux from sediments.
Yeah.
In of milligrams per square meters per second. So would that really mean that there are kilograms of nitrogen being released from each square meter each day, which seems to be quite high?
Yeah, so actually, I did just change to make, sorry to do this to the audience, but were you on the email? Oh, because I've written a much longer thing to Sven and others when this came up about 6 months ago. So it might be worth looking at that again. I think I did change this units just at the last minute in the slide. So apologies for that if it's too high, because I wanted you to be able to see the difference. So I might have the units on that slide wrong, but they won't be in this email. Sorry, that's not as good as it should have been. But anyway, yes.
Yeah, that was just a quick observation. The main one is, I'm just playing with the E-Reefs data in relation to large scale spatial patterns in macroalgal dynamics, and chlorophyll seems to be showing relatively unexpected patterns. Like the plots you're showing do seem to be quite sensible, but in the long-term averages, chlorophyll is notoriously high on the outer shelf reefs compared to the inshore. So I'm just wondering how the individual estimates are validated. SECI seems to produce much more sensible spatial patterns than TSS and chlorophyll, and they seem to be so unrelated. So there are a few things where just not.
Yeah. So, well, I mean, to take on so we do have a large amount of chlorophyll on the shelf edge. It's common, shelf edges that you have upwelling. And actually, I think that the model, so in the model we have when we have this upwelling, we tend to get larger cells that bloom, and larger cells aren't as visible from satellite as smaller ones. So it's quite interesting that, yeah, we have a in situ chlorophyll concentration that might be higher than you might perceive, but if you then calculate what a satellite would see, the concentrations are actually much more moderate and perhaps along the lines of what you think. So I do wonder if there are actually significant increases in chlorophyll on that shelf edge, and maybe we haven't been able to observe them as well as we might in the past, because, you know, they're obviously far off and episodic and all that sort of stuff. So in terms of comparison to observations, we've certainly done a lot more on the inshore ones, and of course that's where, you know, all of Ames's MMP and you know, all the moorings have been put and everything. And so, yeah, so the skill there's you know, reasonable. It's quite a difficult sort of intermittent response there, so it's you know, it's not the perfect match, but I think that the inshore would meet the sort of emergent properties that you might expect. So I do wonder though if there is more chlorophyll offshore than we realise from satellite images.
Mark, there's lots of great praise coming through on the chat for your presentation. There's one question that's come through from Mag095. I have no idea who you are. But the question is, do groundwater-derived nutrients influence the models?
So when we put in loads from the catchment models, right, that is a total load in a river flow. So there's not an underwater, you know, sort of path from somewhere in the catchment popping up, you know, a few kilometres offshore. So that route is not in the model. However, I think the catchment models are trying to account for all of the nutrients coming from the catchments into the water column. So in that sense, we have the nitrogen or the phosphorus that's coming in through that source. Once it's in the water column, I think, so some people think of groundwater being this pore water exchange between the sediments and the water column, even offshore, and that certainly is in there. So, yeah, so I think the total nitrogen that we're talking about in that groundwater is in there. Whether we miss a few details around the coastline by just putting that into a river plume rather than a, you know, groundwater seep, that's possible. Yeah.
One more question that's come through from Gerard Ricardo is whether there are plans to add deposited sediments into the models.
Yeah, sure, that's already there. So in fact, we have two categories of suspended sediments coming out of the river plumes. So one is a larger component which sinks 17 metres a day. One's a finer component that sinks at 1 metre a day. Now, even that breakdown is useful. It would be greater to have a continuum of sizes, because I think that's how the GBR works. But in even having two, we have this ability to drop a whole lot out right at the river mouth while still having a component that goes a further distance. And this is really important for getting secchi depth right, actually, over the inshore regions.
Wonderful. I think that is it from the questions. I've actually got a few more questions, but I'm going to take those offline and probably shoot you an email, I think, in the next few hours. Just lots of stimulated ideas. But I'd like to thank Mark once again for giving up time to present to ACRS today. It's been really informative. I think it's opened up a lot of people's eyes to the power of e-reefs and really what we are learning about water quality and water quality changes and management on the GBR. So thanks once again, Mark, and thanks everyone for taking the time also to join us today.
Okay, thank you.